Determination of instantaneous center of acceleration in plane motion. Article 8.4 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the plane motion of the mechanical body in the flat coordinate axis. X0, Y, X0, Y. So we have the point A, we say the pole, like could be the moving pole of the point A, the radius vector to the pole A. And the point M, which is subject to finding of the total acceleration of the point M. So acceleration AM, the vector of the acceleration of the point M, in the plane of a body, and rotating around the pole is a vector sum two accelerations. Acceleration AA of pole AA of the pole, and the acceleration of the point AMA in the rotation of the body around the pole. So we together have that the acceleration of the point M. This total acceleration is equal to the total of the acceleration of the pole and the acceleration of the point M rotation around the pole. And the acceleration of this we can consider as well, having that the mechanical body rotates with definite angular velocity omega and the angular acceleration epsilon. So we can consider the acceleration of the rotation of the point M around the pole A consisting of two vector sums, tangential acceleration and the normal acceleration directed to the pole A, when the body rotates around the pole A with the angular velocity and the tangential acceleration, because the point M and the body rotates with angular acceleration as well. So the tangential acceleration of the point M equal to the product of the angular acceleration of the body by the arm is AM, and the normal acceleration is proportional, is known as the product of the squared angular velocity omega by the arm AM. So the magnitude of acceleration, the point M in horizontal rotation of the body around the pole A equals, that is the magnitude equal to the arm multiplied by the square root of the total of two sums. The angular acceleration of the body squared and the angular velocity, this is normal part of the angular velocity to force power, because the acceleration normal itself equal to proportional to the angular velocity squared and the arm. And if we consider as squared and squared again due to the Pythagorean theorem, so we have fourth degree. And the position of the instantaneous center of the acceleration we can find as well as having the draft on the figure H42A. So if we have definite point A, which characterized by the translational acceleration AA, the vector on this point A, the body as well, characterized by the angular velocity omega and the angular acceleration epsilon. So all other points acceleration, for example, the point Q, we can find is the vector total of two accelerations of the tangential acceleration of the Q rotation around the pole A and the normal acceleration due to the angular velocity of rotation of the body around the pole A. In the point Q, we have the normal component of the acceleration of the Q related to the point A is proportional to omega squared by the arm AQ. And as well, we have to consider the acceleration translational acceleration to the point A if we transfer this to the point Q. So this is a total of the acceleration action on the point Q. And if point Q could be the instantaneous center of the acceleration, so the this translational acceleration AA have to be equal to the acceleration of the total vector total of the acceleration. So the point Q rotation around the pole A. So we have that if the acceleration of the point Q have to be equal to 0, as we assume that if the Q is the center, instantaneous center of the acceleration, so it possesses the accelerations A of the pole and the acceleration of the point A moving around the pole A rotating. That is, if this is equal to 0, then the acceleration of the point Q rotating around the pole A, around the point A, have to be equal to the translation acceleration of the point Q. Then the total will be equal to 0, and then the point Q will be the instantaneous center of acceleration. So if we next assume that acceleration of the point Q rotating around the point A is the vector total of two components of tangential acceleration of the point Q rotation around the point A and the normal acceleration of the point Q rotation around the point A is proportional to angular acceleration epsilon, is proportional to squared angular velocity omega. Then the magnitude of the QA equal to square root of the squared total. So the tangential and normal acceleration, since AQ, this acceleration, have to be equal to 0, the total acceleration at this point. Assuming that if the point Q would be the instantaneous center of the accelerations, then the acceleration of the point A translation have to be equal to the rotational acceleration by the magnitude of the point Q around the pole, around the point A. Acceleration rotational, I mean the common acceleration of the tangential component, and consistent of tangential, the normal component of the acceleration. Then the length, if we consider this equation, the length of vector AQ, the length, the arm from the pole A. It could be not a pole, but just a point, because we assume that perhaps, yeah, it is a pole. If we consider the total acceleration of the point Q suspected to be the instantaneous center of the acceleration, then this, you can say the A is pole, a pole of the rotation. The vector from the pole A to the instantaneous center of acceleration equals to this ratio. In the numerator, we have the translational acceleration magnitude of the point A, and in the denominator we have square root of squared angular acceleration of the mechanical body and the angular velocity of rotation of the mechanical body to fourth power. Due to this formula, and direction of the vector is determined by the angle mu according to the resulting formula. So we have to find what is, if we have the one direction only. First, as we have assigned the translational acceleration of the point A and the angular acceleration and the angular velocity of the body. So having this only one point and one direction assigned, so we have to find another point which would be Q, the instantaneous center of the acceleration. So we got the distance between this point, the arm, from point A to point Q. And besides, we have to have the direction to the point Q. The direction is the same as we have here, direction, and the right angle triangle. The one leg is the tangential acceleration of the point Q. Another one leg is the normal acceleration of the point Q. Then the tangent of this angle is the relation of the tangential acceleration of point Q rotating around the point A and the normal acceleration of the point Q rotating point. So we have the mu angle here. But another way, the mu angle equal to the direction from the point A, from the positive direction of the acceleration of point A to the point Q. So that is how we can find the direction from any point having the translational acceleration, definite one point, and having the rotational acceleration of the body and rotational velocity of the body, how we can find the point which is the instantaneous center of the velocities. Any mechanical bodies moving and rotating has the definite point, which is of the zero acceleration instantaneously. That point could be or within the body or outside the body, not so much important, but it is in the plane, I mean, for the plane motion. And the magnitude of translational acceleration of the point M equals, this is for the next one decision. Okay, so this how to find the point Q, which would be the instantaneous center of the acceleration to direction. It's a little bit interesting to find the direction, the angle mu, the direction. Directions in the same way. Then we have Q, then we have angular velocity. Angular velocity, if the angular acceleration in the direction coincides with the angular velocity. So the rotating of the body, rotating velocity increases if the acceleration is the same direction than the velocity. But the mu is to the other direction than the velocity. If the angular acceleration of the body contradicts the direction of the angular velocity. So that's how to find the direction of the angle mu. The size we can find by this distant one ratio. And some properties of the instantaneous center of the acceleration. So if we have some points on the straight line, what about the angle? What about the angular velocities here? And if we have a point in another one place, what about the angle mu? Angle mu is from the direction of the translational acceleration of the definite one point to the instantaneous center of the acceleration. So we can see that the angle mu here is depends only on the angular acceleration and angular velocity of the body. So the mu is equal for any point. So mu here, the same angle mu here for the another one point, only on the straight line. And the proportion of the translational or progressive accelerations of the points A, B, C, D, M, etc. So the proportion equivalent to the in the proportion of the arms. So AQ, this is the velocity of AQ, BQ, DQ. This is accelerations translational of any points due to the in the rotation of the instant or the instantaneous center of the accelerations. The proportions of the magnitudes of the accelerations is the same as the proportions of the arms. So the angle mu of the direction between the translational acceleration and direction to the instantaneous center of the accelerations remains for any points of the body, but the magnitude of the acceleration, of the translational acceleration of each point of the body is in proportion to each other, in proportion of the distances to instantaneous center of the accelerations. Two more properties. The first, if angular acceleration of the body is zero, like here we have h43a, and the angular velocity of rotation is not zero. That we have only for the points A and B the normal acceleration says angular acceleration is zero, so the tangential acceleration is component for the tangential acceleration for the total acceleration translational of the each one point with absence of the angular acceleration epsilon. So the points can have with the constant velocity of the rotation of the body can have only the normal accelerations. So then the angle between the direction of acceleration and segment connecting the point A and B and the instantaneous center of the acceleration is equal to zero. So the angle mu equal to zero because with the absence of the angular acceleration, that is a tangent mu equal to epsilon divided epsilon equal to zero, so tangent equal to zero, the angle is equal to zero. This is very understandable. And then the instantaneous center of the accelerations is in the point of the intersection of the lines of the action of the translational accelerations of the points. All points of the body have the same center, instantaneous center, have the same point of the intersection of the lines of the actions of the lines of action, yes, of the accelerations tangent of accelerations translational. So the point will be the same for any point. And another one case, if the angular velocity of rotation is 0, and this is body with not the angular velocity of omega is 0, but we have angular acceleration. Angular acceleration is not 0, then the vector acceleration, I mean that the acceleration of any point, point A, B, point M, maybe of the body M than the previous one figure, but we have here as angular velocity, then we have the angular acceleration. So this is not a sample. The next example for the any point is the direction from any point to the instantaneous center of the velocity is perpendicular to the translational acceleration of the definite one point. So if you have that, this is by the straight line in the intersection. This is into the intersection of the perpendiculars. If omega 0 and epsilon no 0, but the intersection of the lines of the action of the translational accelerations, if the angular acceleration 0, only the rotation velocity we have. And how this goes? Tangent mu is equal to E epsilon divided by squared omega angular velocity of rotation of the body equal to the infinity, because in the second one case the angular velocity is 0. So then mu is the tangent of the infinity is equal to 90 degrees. Pi divided by 2. The same as here we have for the H for 3a, the tangent mu equal to epsilon divided by omega squared equal to 0. And this infinity is 0, have 0. This means that we have 0 angle between the line of the action of the translational acceleration to the direction of the instantaneous center of the accelerations. Questions and comments. Acceleration of the point during the plane motion of a body in the sum of the acceleration of pole and relative acceleration of the point belonging to moving and rotating body under its rotation around the pole. Yeah, it's just the definition that we can consider the acceleration of any point of the moving body, moving and rotating body, as a total. If we have any point translation acceleration, so the translation acceleration of any other point is the total of the acceleration of this any one point, which acceleration translational we know, and the translational acceleration, so the components of translational acceleration of any other point relative to this one, the first one point. This could be the tangential component and the normal component, depending on if the body is of the if the body has the definite angular velocity and angular acceleration. H for 2, the magnitude of point acceleration in the rotational motion relative to the pole of rotation of the body to which the point belongs. The magnitude of the point of acceleration relative to the pole rotation. The magnitude we can find as the magnitude, I mean, that of the arm AM, magnitude equal to AQ, for example, here, is the translation acceleration of this point divided by square root of the squared angular acceleration of the body plus angular velocity of the body fourth degree in the denominator under square root. H for 3 translation, the instantaneous center of body acceleration performed in plane motion is the point of which acceleration is 0. Yeah, the definition of the instantaneous center of the body acceleration. 8 for relativity of acceleration is opposite in direction and equal in magnitude of the instantaneous center of acceleration is the point of body moving with acceleration. This is criterion how to find the instantaneous center of the body acceleration. The criterion is that equality of the, if we have any point with the translational acceleration, the criterion of any other point to be the center of the instantaneous, to be the instantaneous center of acceleration with 0 acceleration, that is the relative part of the acceleration, the tangential acceleration and normal acceleration of the each point subject to consider as the instantaneous center of the acceleration. Its relative acceleration components are tangential and tangential and normal in the vector total. In the vector total have to be equal of the translational acceleration of the point relative to which we got the translation, the normal and tangential acceleration of the point subject as to consider as would it be the center of the instantaneous center of the acceleration. So relativity of the acceleration, yeah, the opposite direction, the called magnitude of the instantaneous center of acceleration, the point of body movement. That is this criterion. H45, proportional to the angular acceleration of a body and the distance between each point of body and the instantaneous center of the acceleration, the tangential relative acceleration of its points and its instantaneous center of acceleration relative to these points. So if we have the moving body with definite angular velocity and definite angular acceleration, and we have for this body we have the instantaneous center of the acceleration, so the any point acceleration would be equal, proportional to the distance from the instantaneous center of acceleration to this point, the magnitude of this point, and the direction will be to the arm, to the radius from instantaneous center of acceleration to definite one point, to this radius will be inclined for the same angle mu for all the body. So the direction of the translational acceleration of any point of the body is to the direction from this point to the instantaneous center of acceleration of the body would be at the same angle for the any point of the body. Mu, no, we can got it having the tangential and acceleration and having the angular acceleration of the body and having the angular velocity of rotation of the body just as an argument of tangent of the ratio of the angular acceleration of body to squared angular velocity. H46, proportional in the square of angular velocity and the distance between each point of the body instantaneous center of acceleration, the normal acceleration relative to the point and the instantaneous center of acceleration relative to this point. Proportion to square angular velocity, yes. So as we have the instantaneous center of acceleration, the acceleration normal and acceleration tangential of any point will be proportional to the distance from this instantaneous center of acceleration to the consider it any one point, but only the factors are other. As for the normal acceleration, the factor is squared angular velocity of the body rotation, and as for the tangential component of any point acceleration, the magnitude of the tangential component will be proportional to the arm as well from the instantaneous center of the acceleration to the definite one point, and proportional to the for the tangential proportional to the angular acceleration of the body rotation. H47, finding the distance to the instantaneous center of velocities from the given point of the body motion with acceleration of the direction of the instantaneous center of accelerations in relation to the direction of acceleration of this point. The direction angle depending on the ratio of tangential and normal relative accelerations of the point and the instantaneous center of the acceleration. Yeah. The distance from any point to the instantaneous center of acceleration equal to the translational acceleration of the definite one point, and in the denominator we have the square root of the squared angular velocity of body rotation, angular acceleration of body rotation, and the angular velocity of body rotation power to 4, and the angle of the direction of the from the acceleration direction, What in point A, for example, the angle is argument tangent of the ratio of the angular acceleration of the body rotation to the squared angular velocity of the body rotation. H for H, the direction of the instantaneous center of acceleration lies on the line of the acceleration of the point if the angular acceleration of the moving body to which a point belongs is equal to 0. In this case, the tangent central acceleration lies at the intersection of acceleration directions of any 2 points of the body. Yeah, if the angular acceleration of body equal to 0, so the body rotates with the constant angular velocity, then any point of the body has any point of the body has only normal component of the acceleration directed to the instantaneous center of the accelerations. 8, 4, 9. The angle, if the angular velocity of rotation of the body to which the points belongs is equal to 0, yeah, 8, 4, 9, then the normal component of the acceleration of any point of the body equal to 0 if the angular velocity of rotation of the body when the points belongs is equal to 0. And the angular acceleration is not equal to, yeah, then that any point besides of the instantaneous center of the accelerations, any point of the body rotating with acceleration, but with 0 angular velocity initial. So in the next, the velocity angular will not be 0 because due to the angular acceleration. But in this case, the direction to the instantaneous center of acceleration is perpendicular to the direction of acceleration of the point, in this case, the instantaneous center of acceleration lies in the intersection perpendiculars to the directions of acceleration of any 2 points. Yeah. So if we have 0 angular velocity, we have only angular acceleration. So the begin of the rotation of the mechanical body and having the angular acceleration and having the acceleration of 2 points, we can find the perpendiculars, and in the point of the intersection, we have the instantaneous center of the accelerations. Otherwise, if we have 0 angular acceleration of the body and we have definite magnitude of the angular velocity of the body, so any point have only the normal component of the acceleration, and they intersect in the point of location of the instantaneous center of the acceleration. Thank you.